Welcome back to another lesson, and what you will learn today is how a simple pendulum is a wonderful example of simple harmonic motion. Well, strictly speaking, we'll stay in that small angle world where the SHM model for pendulum works beautifully. So, what we have is a mass m hanging from the ceiling by a string of length L. Now imagine we pull this mass to the right by a small angle theta, and let us find what are the forces acting on this mass. Well, one is quite obvious, and that is gravity mg pulling it straight down. The second is tension T pulling up along the string towards the pivot. Now instead of tilting our heads, let's use a standard x and y coordinate system. Next, we break tension T into its respective components, and if the angle at the top is theta, then this angle is also theta. So you can see the vertical component pointing up is T cos theta, and the horizontal component pointing to the left is T sin theta. Now let's apply Newton's second law to the x direction first, and we see the only force in the xx direction is this one. So we write minus T sin theta is equal to max, where ax is nothing but the acceleration in the xx direction. And why the minus sign here? Simply because if the displacement x is to the right or positive, the force is pulling to the left or negative. So you can say it's a restoring force. In other words, this minus sign is a mathematical proof that the system wants to return to equilibrium. Also, look at the geometry of this triangle. Sin theta is the opposite side over hypotenuse. That's x upon L. So let's substitute that in here, and let's call this equation 1. Now let's look at the y direction. The mass is moving down, then up, but does it accelerate much vertically? Let us find that out. So we have T cos theta pulling up and mg pulling down. So using F is equal to ma, we get T cos theta minus mg is equal to may. Now here we make some clever approximations that will actually make our lives a lot easier. So the first one is called the small angle approximation. That is, we assume the pendulum swings a tiny bit only, say less than 10 degrees. Now if theta is small, like 5 degrees or 10 degrees, cos theta approximately equals 1. Because if you check cos of 5 degree, it equals 0.996, almost 1. And if you calculate the error of this approximation, it would be about 0.4%. Even cos 10 degree is about 0.985. That is also quite close to 1, or an error of about 1.5%. So smaller the angle, closer the value of cos theta to 1, and that makes the approximation even stronger. And there's another famous small angle fact that we will use while solving problems later, and that is, for small theta in radians, sin theta approximately equals theta itself. For example, sine of 0.1 radians is actually approximately equal to 0.1, or sine of 0.2 radians is approximately equal to 0.199, and so on. The second approximation is that for small oscillations, the mass hardly moves up and down, and therefore the vertical displacement is much smaller than the horizontal displacement. So the net vertical force and therefore the vertical acceleration is very small. In fact, I calculated that for a 10-degree pull, the vertical acceleration comes out to about 0.3 meters per second square, which is only about 3% of g, which is 9.8 meters per second square. So we treat the vertical acceleration as negligible, and we can safely assume ay is approximately equal to 0. So if we take these two approximations into consideration, what happens to equation 2 is t into 1 minus mg equals 0, or t equals mg. So the important takeaway is that for small swings, the tension is essentially equal to the weight. However, I must add here that in the exact motion, t is not always exactly equal to mg. Actually, at the bottom, t is slightly larger than mg because it also has to provide the centripetal force for the circular motion this pendulum is undergoing. And at the extremes, t is slightly smaller than mg. But for small swings, these differences are just a few percent. So treating t approximately equal to mg is an excellent approximation and makes the SHM structure pop out very nicely. Okay, now take this value and plug it back into equation 1 to get minus mg into x upon L is equal to max. And we are left with ax is equal to minus g upon L into x. So does this equation look familiar? Well, it should, because this is the hallmark of an equation that represents simple harmonic motion, or a is equal to minus omega square x. And here our acceleration is proportional to displacement and opposite in direction. And by comparing the two equations, we can see that our constant term omega square is nothing but g upon L, and that gives us the angular frequency omega equal to root of g upon L. And finally, since period t is equal to 2 pi upon omega, t equals 2 pi root of L upon g. And notice what's missing. Well, it's a mass. And I think that is magical. Well, why do you think this happens? The answer is simply because gravity pulls harder on massive objects, that is mg, but more massive objects are harder to move, that is ma. That is, the two effects cancel out perfectly. Another interesting thing you should notice is that our formula is actually independent of amplitude. But you must remember, only for small swings. For larger angles, say 40 degrees or 60 degrees, the period gets a bit longer than this value. Also, look at g, that is in the denominator. If g gets smaller, the period gets bigger. So if you took this pendulum to the moon, where the gravity is weak, or into outer space where g is near 0, what do you think happens? Well, on the moon, it swings in slow motion. In deep space, where g is 0, the pendulum wouldn't just take forever to move, it would simply float, because without gravity, there is no restoring force and therefore no oscillation.